We've made it to episode 20, the last episode of season 1. I really hope you've enjoyed these videos, and if they ever really get popular, I promise to make many more. To that end, if you want to do me a solid, maybe you could share them with some friends, or post about their existence on some social media platform that I'm way too old to use. Or not, whatever, no pressure. Anyways, the last puzzle for this season is one that I find really fun. Because I enjoy alliteration, I'm going to call it Televising the Tendencies of a Timid Traveling Tribe. Here's how the story goes. You're a scientist, and there's this fascinating tribe of people that you really want to study. They live on a 1 mile by 1 mile square plot of land, and there's only 2 options for how this tribe will proceed. Either they'll stay on this 1 by 1 plot of land forever, or they'll get into an argument and split. If they get into an argument, every single person in this tribe will leave their original square plot of land, and exactly half of them will move to an identical 1 by 1 mile square plot of land directly north, while the other half will move to an identical 1 by 1 square plot of land directly east. Nobody stays put. The original square plot of land is completely vacated. We now have 2 tribes inhabiting their respective plots of land, and each live by the exact same rules. Either they stay in their respective plots forever, or either one or both of them can split. If the group splits, half move north, half move east, and where they're coming from is vacated. This continues as long as we want. And you're like, okay, I guess I see how these are traveling tribes, but what makes them so timid? Well, here's the thing. A given tribe won't split if some other tribe currently occupies the land due north or due east that they would be moving to. So in this example, this tribe can't currently split. However, if the tribe north of them split, then the land north and east of them would become vacated, so now they'd be able to split. Make sense? Okay, I understand how these tribes are timid and how they travel, but what's this part about televising their tendencies? Well, you, the scientists, are going to set up cameras to record these people. Each camera can record one of these plots of land. You set up the cameras before the tribe ever splits. All you need to do is record one tribe, you don't care which one, indefinitely. My question to you is, what is the least number of cameras that you could use to guarantee that at least one of them would record a plot of land inhabited by one of these tribes after all the splitting is done? It's a harder question than you might think. My intuition was way off. As always, you might consider pausing the video and playing with it on your own for a little while. It's worth recognizing that I first heard about this problem from a Numberphile video. Dr. Stankova, who I believe teaches at Mills down in the Bay Area, did a really good job with her video. And while I'm going to approach it a little bit differently, I'd be remiss if I didn't at least shout her out. And on the topic of shoutouts, most of the results that you'll see in either her video or this video come from this paper, which is a fun, although a bit complex, of a read. But noteworthy is that one of the authors is Ronald Graham, a super interesting guy, famous for a lot of things, but maybe most notably Graham's number, which holds the record in the Guinness Book of World Records for the largest number ever used in a serious mathematical proof. It takes a little bit of work to understand it, but if you really want to get into it, I gave a presentation about Graham's number that I turned into these 5 videos that you can check out if you want. Anyways, back to our problem. Maybe an example will help. Suppose we set up cameras to record these 10 plots of land. Again, our tribe starts out down in the southwest corner, and I suppose I should let you know that the land continues infinitely far to the north and to the east. In fact, we could superimpose some axes and think about the land as the first quadrant of a plane, referring to the plots of land by the Cartesian coordinates marking their centers. All I'm saying is that in this example, we're recording 0, 0, 1, 0, 2, 0, and 3, 0, 0, 1, 1, 1, and 2, 1, 0, 2, 1, 2, and 0, 3. And as always, the tribe starts out down at 0, 0. And the question becomes, are we guaranteed to be recording a plot of land where a tribe ends up? Another way to think about it is, if you are in control of the tribes, can you move them according to their rules for movement to completely escape the green area that's being recorded? If not, then we're guaranteed to be recording a plot of land where one of the tribes ends up. Not that you care about my initial thoughts, but when I saw this before I tried it, I figured, yeah, sure, that'd be super easy. Just sort of keep splitting the tribes so that they move further north and further east. But if you try it, it turns out it's not as easy as it sounds. And if you try it enough, you might convince yourself that it's not even possible, that this configuration is guaranteed to record a tribe. But how would you go about proving such a thing? Just saying, I tried for a long time and couldn't figure it out is a pretty unsatisfying proof. Well, it turns out that no, the tribes never can escape the green area, and that there's a super elegant proof of that fact. The argument is typically credited to a brilliant mathematician and Fields medalist known as Maxim Kontsevich.
It's my life, and it's the thing which I do the best. I will be never tired of mathematics. So beautiful and endless, yes.
What Maxim did is make 3 key observations. The first was to recognize an invariant in this problem. If we go all the way back to the starting square, we see 100% of the tribe in the plot of land we're calling 0, 0. I'll just put a 1 here because I don't want to deal with percentages. After the first split, half the tribe goes to 1, 0, and the other half goes to 0, 1. But note that the sum is still equal to 1. If we split one of those 1/2s in half, we create 2 1/4s, but again, the sum is equal to 1. It doesn't matter how many times the tribe splits. If we're tracking the fraction of the original tribe that currently inhabits any given plot, the sum of these fractions must be equal to 1. This sum is invariant to the operation of the tribe splitting. This first observation leads into his second key observation of this problem, that the number of splits necessary to get to any given plot of land is just equal to the sum of the x and y coordinates of that plot. Consider the plot of land at 2, 4, for example. 2 plus 4 equals 6, and to get a tribe to inhabit that plot of land, the original tribe would have to be cut in half 6 times. What that means is that if this plot of land is ever inhabited, it's inhabited by 1 divided by 2 to the 6th power of the original tribe. Similar logic allows us to figure out the fraction of the original tribe that would inhabit any square on our grid if that square is inhabited. Maxime's third and final key observation was to notice that the sum of all these fractions is 4. Okay, that's a bit of a lie. If you were paying attention earlier, you might remember that these plots of land continue infinitely far to the north and to the east, so there's infinitely many of these fractions. We can't really add up infinitely many things, but we can talk about the limit of this infinite sum. Maxime calculated this limit to be 4. Infinite sums, limits, this might sound really intimidating if you haven't seen any calculus, but it's really not that bad. Let's start by considering the sum of the infinitely many fractions in the first row of this grid. We don't know the value of this infinite sum, so let's name it s so we can set up an equation. A cool thing happens when you multiply both sides of this equation by 1/2. All of the terms on the right side of the upper equation, except for the leading 1, show up on the right side of the lower equation. My lower equation tells me that these terms are equal to half of s. So I can replace the infinitely long tail in the top equation with that 1/2 s. All of a sudden, instead of infinitely many terms, my equation only has 3. It's easy enough to solve this linear equation to figure out that s is equal to 2. We can do this exact same trick on the second row of our grid to figure out that this infinite sum is equal to 1. And if we use this trick on the third row of the grid, we see that that infinite sum is equal to 1/2. You can continue to use this trick if you want, or maybe you just recognize the pattern to figure out the values of the sums of the rows of this grid. We're making progress, but because there's infinitely many rows, if we want to know the total value of all of the sums in the grid, we have to sum these infinitely many subtotals. Fortunately, our new trick works perfectly once again, and we find that the sum, or more accurately the limit of the infinite sum, is equal to 4. Pretty cool, huh? Anyways, with these 3 observations, we can now prove that it's not possible to move a tribe completely out of the green squares. And therefore, if we place 10 cameras to record these 10 squares, we're guaranteed to record a tribe after all the splitting is done. Can you see why? If you add up the fractions in the green squares, you get a sum of 3 1/4. We know that the sum of all the squares is 4, so therefore the sum of the non-green squares is just 3/4. But the sum of the squares that the tribe's going to inhabit is always 1. There's only room for 3/4 in the non-green squares. We can't possibly fit the whole tribe. The bad news is that we have not yet answered the question of what the least number of cameras is that would ensure we'd be able to record the tribe after all the splits. But the good news is that we have an upper bound on that answer. We've shown that we can certainly do it with 10 cameras. But could we do it with less? Let's consider the case where we have cameras in these 6 squares. Using the same method as before, we see that the sum of the fractions in the green squares is now 2 3/4. Therefore, the non-green squares are able to accommodate 4 minus 2 3/4, in other words, 1 1/4. That's good news. The tribe only takes up an area of 1. We've got enough room, right? Well, not necessarily. Just because we can't use Maxime's method to prove that a tribe couldn't possibly fit outside of the green squares doesn't mean that a tribe necessarily can fit out of the green squares. You can try it for a little while if you want, but spoiler alert, don't spend too much time because it's impossible. Whoa, wait, why? What's going on here? What Maxime's observation tells us is that if we could use all of the squares that are not green, there'd be enough room to hold the entire tribe. But there's no way to use all those squares. One issue is that because of the way the tribes split, there'll never be more than 1 square in the first row occupied by a tribe. Recalling that the sum of all of the fractions in the first row were 2, and that a 1, a 1/2, and a 1/4 are in the first row in the green area, there's a total area of 1/4, not in the green area in the first row. Since we only use 1 cell in the first row, at most we're using 1/8, so the remaining 1/8 can't possibly house the tribe. The exact same logic works for the first column, which has a total area of 2, 1 3/4 of which is in the green area, so 1/4 of which is not in the green area. The way the tribe splits ensures that there can never be more than one square in the first column occupied by the tribe. The most the tribe can get out of the first column is 1/8, and the remaining 1/8 area is also unoccupied by the tribe. We started with an area of 1 1/4 outside of the green area, but subtracting these 2/8 leaves us with an inhabitable area of just 1, the exact same size as the tribe. But that inhabitable area of 1 is comprised of infinitely many cells. The tribe can only live in a finite number of cells, so there's not enough inhabitable room for the tribe outside of the green area. If you don't like that finite infinite argument, note that in order to have the tribe in the 1/8 spot in the first row, there must be exactly 3 cells in the second row that are occupied. Therefore, there are cells in the second row that are unoccupied, so the tribe is not using all of the inhabitable cells in the grid, meaning what they are using has an area of less than 1, which isn't enough to house the tribe. What I'm saying is that the tribe can't possibly escape these 6 green cells, meaning that we've reduced the upper bound for our answer from 10 to just 6. Okay, cool. We've made some solid progress reducing our upper bound. Maybe it would make sense to see what kind of lower bound we can come up with. To do so, it'll help to incorporate 2 key results from the paper that I referenced at the start of this video. The first is that the tribes can end up occupying a set of squares in our grid under the normal rules of our game if, and only if, the tribes could get there under a slightly modified version of the rules of our game. I'll let the animation show a set of squares that we can reach under the normal rules of the game, while I explain the rules for the modified version. The modified version of the rules allow a tribe to move onto a square that's already occupied, as long as they eventually leave that square. So it's fine to have multiple tribes on a given square, we just can't stop splitting until all squares have either 0 or 1 tribe on them. Let me demonstrate. As always, our tribe starts in the bottom left-hand corner. I'll indicate that there's a tribe there by putting a 1. We don't want any tribes to end up there, so I have to make that a 0. I do so by splitting this tribe. However, instead of putting a 1/2 on squares 1, 0, and 0, 1, I'm going to put a 1 on those squares, because I'm not concerned with what fraction of the tribe resides on those squares, but rather the number of different tribes that currently reside on each of those squares. Our normal splitting rules didn't leave any tribes on either of these squares, so we want to split both of them. Note that when we do so, we end up with 2 different tribes on the square 1, 1. This wasn't allowed under our old rules, but it's perfectly fine now, as long as we eventually move one of those tribes off that square. Looking at our newly occupied squares, both 2, 0 and 0, 2 are not supposed to end up with any tribes, so we need to split each of these 1s to make them 0s. However, 1, 1 is supposed to end up with a tribe on it. We currently have 2, so one of those 2 needs to split. We continue in this fashion, taking things 1 diagonal at a time, leaving a 1 on all squares where a tribe is supposed to end up, and a 0 on all squares where a tribe is not. Now, it's worth pointing out that all I've done is demonstrate these new rules to you. I certainly haven't proven that just because you can reach some configuration with these new rules, that you could also reach them with the old rules. And I'm not gonna prove that to you, but maybe it's not that big of a leap of faith. The way I like to think about it is that if I end up with some configuration with these new rules where tribes are allowed to overlap, I can do the exact same splits but in a different order, loosely speaking, forcing all the tribes as far out to the north and to the east as quickly as possible. Since I'm doing the exact same splits, I'm going to end up with the same final configuration, but by changing the order, I can avoid all the overlapping. Anyways, if you'll grant me that these 2 games are equivalent in terms of their outcomes, we're just 1 observation away from getting our final answer. That final observation is that if I play with these new rules, splitting the tribes 1 diagonal at a time as I just showed, not worrying about overlapping, knowing that I'll eventually get all the tribes on their own square, I can test whether an ending configuration is possible by just looking for numbers greater than 2, squares that have more than 2 tribes on them at any given moment. Again, let me demonstrate. Because we've already shown we can't escape these green squares, a configuration like this should be impossible. A way to see that it's impossible is by trying to create it with our new rules, working 1 diagonal at a time, and seeing if we run into any numbers greater than 2. We could continue splitting the tribes, leaving 1 on all the squares that are supposed to end up with the tribe, but we don't even need to. We see a number greater than 2, so this arrangement is not possible. You might wonder why a 3 is enough to indicate that an arrangement is not possible. Well, I like to think about it like this. If you're working along the diagonals like I've demonstrated, at some point you come to your first 3. I'll put it here for the sake of the animation. Think about how that 3 came about. There's 2 different cells that feed into it, but neither of these cells had a 3 because, again, this is our first 3. So we must have gotten 2 from one of the cells and 1 from another cell. The 1 might have come from the case where there was 1 tribe and we needed 0, or where there was 2 tribes and we needed 1. It doesn't matter. The key thing to realize is that the cell that contributed 2 to this 3 also contributed 2 to a cell right next to it on the diagonal. What that means is right next to each other on a diagonal, we have a 3 and a cell that has at least 2. This is problematic. A 3 with a 2 next to it can never reduce. That's because the most we can leave on any cell is 1, so when the 3 splits, it sends out 2s. But the 2 also needs to split, sending out 1s, which will create a 3 and a 2 next to each other on the next diagonal. We can never reduce this 3 and this 2, so we can never get to a legal configuration. But wait, there's an even more powerful result. Remember, our goal is to see if we can have a tribe escape the green area. If we've applied our new rules along the diagonals and we've surpassed all the cells in the green area, if we don't see any cells that are greater than 2, then we're guaranteed to be able to reach a configuration that contains only 0s and 1s. We need a visual. Suppose we have some combination of green and non-green cells in here, and we've applied our new rules along the diagonal until we've gotten past that area. And on this last diagonal, we don't see any cells greater than 2. Well then, worst case scenario, all of the cells on the diagonal are 2, except for the one in the first row in the first column, which can never be greater than 1. Remember from before, the way our tribe splits, we can never have more than 1 in the first row or the first column. This worst case configuration of 2 1s and a bunch of 2s reduces to just 0s and 1s. It works because of the fact that we're past the green cells. What that means is we're allowed to leave a tribe in any other cell that we want to. When we split, most of the 2s remain 2s, but the ones furthest out on the diagonal, thanks to the fact that they neighbor 1s, turn into 1s. And if we split again, we'll see the same thing where most of the 2s stay 2s, but 2 of them will turn into 1s. This will continue to happen until all of the 2s turn into 1s, and we end up with an allowed configuration. I know that's a lot of theoretical stuff, but we can use it to finally answer our question. Before I introduced these alternative rules, we saw that 6 was an upper bound for our solution, meaning that if we had 6 cameras, we could sort of load them up down in the bottom left-hand corner and guarantee to record a tribe once all the splitting was done. But what we have not figured out is whether we could do it with less than 6 cameras. Let's start by getting greedy. What if you only have 1 camera? Is there anywhere you could put it to make sure you'd record the tribe? Well, no, because you'd have to put it at 0, 0. Otherwise, you'd never see a tribe that never split. But if it's at 0, 0, it's easy enough for the tribe to escape it by just splitting a single time. Clearly, 1 camera is not enough. What about 2 cameras? Well, again, we need one of our cameras at 0, 0 to protect against the case where the tribe never splits. And then our second camera would either have to go on 1, 0 or 0, 1, because otherwise that tribe that just splits a single time escapes our view. But whichever one we put it on, we can just have that tribe split one more time, leaving the other tribe alone to escape all the cameras. So 2 cameras isn't enough either. What about 3 cameras? Well, again, clearly you need one at 0, 0 to ensure against the tribe that never splits. But I claim you also need one at both 0, 1 and 1, 0. Because, for example, if 1, 0 is missing, then we can completely ignore the first row, because the only tribe in the first row is not on a square that's being recorded. But if we completely ignore the first row, our grid looks a lot like the original grid, with a tribe in the lower left-hand corner, and we only have 2 cameras left. A minute ago, we concluded that there is no way to guarantee we'd be recording a tribe under this situation. So we don't even have to follow through with our analysis, we've already done it. Okay, but what if there are cameras at 1, 0 and 0, 1? Well, then both of those tribes would have to split, leaving us with this scenario and no cameras left. As long as we can turn this into a legal configuration, we've shown that 3 cameras isn't enough. It's easy to turn into a legal configuration. Just have one of the tribes at 1, 1 split. And I guess really you didn't even need to do that, because we showed earlier that once we're on a diagonal that's past all the green cells, as long as none of those cells are greater than 2, we're good. At any rate, 3 cameras is not enough. What about 4 cameras? Well, we kind of do the same analysis. We have to put a camera at 0, 0, just in case a tribe never splits. We have to put a camera at both 0, 1 and 1, 0, because if either of those 2 are missing, we either ignore the first row or the first column, and it looks a lot like our initial configuration with 3 cameras, which we've already shown doesn't work. So there must be cameras at both 0, 1 and 1, 0. Before we worry about where to put our 4th camera, let's recreate what would have to happen for there to be no tribes on these green squares. And now that the tribes have escaped 3 of the 4 cameras, let's split one of the tribes at 1, 1, because we know we can't possibly end up with 2 tribes there. Staring at this configuration, can you convince yourself that with only 1 more camera left, there's no way to guarantee we record a tribe? I mean, we'd have to put that camera on one of the squares with a 1 on it. Otherwise, we can just leave the tribes right here and escape the cameras. And then whichever of those squares we put the camera on, we just have that single tribe split, which would leave us with only 1s and 2s, which, as we've already shown, ensures that we can't possibly guarantee we'd be recording a tribe. So 4 cameras isn't enough either. That means the lower bound for our solution is 5, and the upper bound for our solution is 6, which means we're getting really close to our answer. Let's play with 5 cameras. if we can figure out a configuration that would guarantee we'd record a tribe, then we're done and the answer is 5. And if we can't, well, then we're still done and the answer is 6. The first part of our analysis is the exact same as we've seen in the previous 2 cases. We have to throw a camera at 0, 0 in case the tribe never splits. We have to throw cameras at 1, 0 and 0, 1, because if not, we can imagine that we're in the initial configuration with only 4 cameras, which we've already shown is not possible. So we're back to this configuration, this time with 2 cameras left. We'll again split one of the tribes on 1, 1 because we know we'll have to split them eventually to get to this grid. We have 2 cameras left, and our goal is to place them in spots that will create a square having 3 tribes on it. Can you do it? I bet you can. One option would be to put one of the cameras here at 1, 1 and the other one up here at 0, 2. To avoid the cameras, each of these tribes would have to split, but each of these splits would add another tribe to 1, 2, which already has a tribe, giving that square 3 tribes total. As we saw before, this 3 will never be able to reduce, so there's no way we can end up in a legal configuration. What I'm saying is that if we have cameras on these 5 squares, we're guaranteed to be recording a tribe once all of the splitting ends. So finally, the answer to our question is just 5. There's at least 3 other really interesting results from this paper that I'd kind of like to share with you, but this video is getting pretty long, so I better end it here. For the final challenge question of the season, I want to make the point that I just showed you one way that we could place 5 cameras and guarantee we'd record a tribe. It's not the only way you could place 5 cameras and guarantee you'll record a tribe. My question to you is, can you find all the different ways that you could place these 5 cameras and guarantee you'd record a tribe? For bonus points, can you show that there couldn't possibly be any more? As always, I'll check out the comments to see if anybody has any questions, thoughts, or solutions.